In this video, we will go over problems in week 1 practice that are focused on the number theory. First, let's look at problem number 1. The problem says n is the smallest positive integer whose digits add up to 2022. Then what is the sum of digits of n plus 1? So first here we see, in order to get the smallest, what we need is the least of digits of n is as less as possible. That means we should use as many as 9 as possible, right? Okay, so first we know. So what we here is we should use as many as 9 as possible, right? Okay, so then all we need to do is we see, all right, so how can we split 2022 into nines? And then we use this to divide by 9, right? So here is 18, 22, so it's 2. Again, okay, so this 18, and this is 42, and then we have 4, right? 6. Okay, so the remainder is 6, right? Okay, so from here, we know what should be n. So n, because we want to the smallest, so should put a 6 in the front, and then we should 999. Okay, so how many 9 should we use? We should use 224 nines, right? Okay, so that is the smallest n we can get. And then if n plus 1, so okay, what is n plus 1? Then we just get a 7, 0, 0, 0. And how many do we have? 2024. Okay, so then the sum of digits will be 7, right? 7 will be the sum of digits of n. Question number 2. In a group of children, the ratio of boys, okay, ratio of boys to girls is 3 to 5. After n boys join the group, the ratio becomes 5 to 3. The question is, what is the least number of n? So n is the number of boys, right? The number of boys that later join the group. All right, so here, first of all, we realize the number, there's one quantity that does not change, which is the number of girls, right? All right, so first we realize the number of girls does not change. All right, so let's use a little algebra to make things easier to handle. Okay, so here I let x is just the number of girls that does not change, right? And then we say, okay, so then we have at the beginning, the number of boys. The number of boys equals, because here the ratio says is 3 to 5, well, which is the beginning is 3 to 5. So the number of boys will be 3 to 5 times x, right? And then later, right, that means after you add this n new boys, then later, the number we get, okay, later, the number of boys becomes, because it's 5 to 3, right? The ratio between number of boys to the girls, the 5 to 3. So it'll be 3 or 5, 5 or 3 times x. Okay, and then we say, okay, what's the n? Then we say, okay, n it just equals 5 over 3x minus 3 over 5x. Now, the number of boy has to be an integer, right? From here we say, okay, it has to be integer because both of them has to be integer. So we get x must be divisible by both 3 and 5, right? By both 3 and 5. Therefore, you see here what we are looking for is the smallest. We are looking for is the least number of n, right? So it's the least number of n. So first of all, so from here we get this one. We get x is at least 15, right? So which is the LCM of 3 and 5, right? At least 15. Okay, so if we put a 15 here, so this will give us the least value of n, and which is 25 and minus 9, that is 16, right? So 16. Okay, question number 3. What is the largest 3-digit number that has the form? So it's 3-digit. The middle number is 5, and that is divisible by 12. Okay, so first of all, let's see. What shall be the divisibility criterion for 12 because 12 equals 3 times 4, right? Okay, so this implies this guy, so this 3-digit number is divisible by 12 means this one is divisible by both 3 and 4, right? Because 3 and 4, they are coprime, and 12 is 3 times 4. And now we can apply the divisibility test for 3 and the divisibility test for 4. Let's recall this. Let's recall the divisibility test. For 3, that if we, in order to tell whether the number is divisible by 3, we have a shortcut. So that's so-called divisibility test. The shortcut says all we need to do is look at the sum of digits. Right? A number is divisible by 3 if and only if the sum of digits is divisible by 3. Okay, let's recall this. All right, so here says a number n is divisible by 3 if and only if sum of digits is divisible by 3. And this is also true if we replace 3 by 9, right? So the divisibility test for 9 is the same. You just look at the sum of digits divisible by 9. Now let's look at 4. What's the divisibility test for 4? N is divisible by 4. All we need to look at is the last 2 digits, right? We just if and only if the last 2 digits, if we use the last 2 digits to form a 2-digit number, last 2 digits as a number, right, is divisible by 4, right? If you look at the last 2-digit number, the last 2 digits, they form a 2-digit number. So here, let me make it more precise. As a 2-digit number is divisible by 4. Okay, now let's look at here what we have. So we have A, 3, 5B, right? So first of all, let's take care of 4. As we said, we just need to look at the last 2 digits, right? In order for this one to be divisible by 4, we know we have 2 choices. Either we can have 5, 2, which means B is 2, right? This is divisible by 4. Or we can 5, 6, right? So this means B equals 6, right? Okay, but meanwhile, look, we want to make the number as large as possible, right? And then you see, if I use, so case 1, right? Case 1. If I use, say, 5, 2, the last one is it's a 2. And then in order to make it to be divisible by 3, so 5, 2 plus 7, and okay, the largest one I can go, this is 8, right? So this will be the largest I can make because 7 plus 8, which is 15, this is divisible by 3. Now, case 2, suppose I go with 5, 6. And then we know 5, 6 is what? 5, 6 is plus is 11. Well, in order for the sum to be divisible by 3, if you want to make it as large as possible, then what we can do is, okay, we can put it's 5, right? We can put it's 5. And that's what we can do because, we can put it's 4, right? You can put it 7. We can put it, because we want to make it large as possible, so we can put it 7. Because 7 plus 11 is 18. This is divisible by 3. Now, since we are looking for the largest, so this is what we can do, is 8, 52. So this is the largest one we can go. Okay. Now, of course, if we just want to find the 3-digit numbers like this that are divisible by 12, they are more than 1. But here we're looking for is the largest. Problem number 4. The reverse of a number of 14 is 41, and they add up to 55, which is divisible by 5. How many 2-digit numbers AB that has the property that if AB plus BA, right, we just reverse it, right? AB plus BA, this one is divisible by 5. Okay, so here we require, when you reverse it, it's still a 2-digit number. So that means 5, 0, this is not allowed because if you reverse 8, you get 0, 5. This is not a 2-digit number, right? It's not a 2-digit number. So we do not allow 50. Okay, anyway, let's recall when a number is divisible by 5, we know, okay, so let's recall the divisibility test. Divisibility test for 5. A number is divisible by, in order to tell where the number is divisible by 5, all you need to do is look at the last digit, right? If the last digit is 0 or 5, then it's divisible by 5, right? N is divisible by 5 if and only if the last digit is 0 or 5, right? Okay, now let's look at this. So we have here, what we have is, it's AB, right? So here we have AB plus BA, and then you see the last digit is given by A plus B, right? So given by A plus B. And okay, in order to have 0 or 5, what can we have? We have either A plus B equals 5, or A plus B equals 10, or A plus B equals 15, right? And then, of course, you can just find all the combinations. So this is 1 plus 4, this is 2 plus 3, 3 plus 2, and 4 plus 1, right? 4 plus 1, because here the order matters. And A plus B is 10, it's 1 plus 9, right? And then 2 plus 8, and all the way to 9 plus 1, right? 15, because A and B, they are both one-digit numbers. What you can do is you can have 6 plus 9, right? And you can 7 plus 8, right? All the way to 9 plus 6. And then you find all what was the total number we have, right? So here we have 4 of them. And then here we have, let's see, 9 of them, right? And here again, we have 4 of them. So if you add all together, which is 17, right? 17 is the total number of such kind of two-digit numbers. Problem number 5. For how many positive integers n, that is between 1 and 200? So here we have 3 over n and 4 over n, right? 3 over n and 4 over n, they are both fractions in the simplest form. Now, what does it mean as simplest form? Which means we cannot reduce this fraction by dividing a common factor. Right? Therefore, here you see what we have. This problem basically just says, okay, what we have is 3 and n are coprime. They do not have any common factor except 1 to simplify, and the 4 and n are also coprime. Okay, you see, then this just means n is not divisible. So n is, because 4, we know just 2 times 2, and 3 is already a prime number, and this just means n is not divisible by 2 or 3. All right, so you see this problem is basically saying we are looking for positive integers n between 1 and 200, and that is not divisible. By 2 and 3. Okay, let's see this. Here we know in total we have 200 numbers, right? 200 numbers. That's right here. So 200 numbers. And then what we want to get rid of is those numbers divisible by 2. Okay, so let's see, divisible by 2. And then we look at the numbers that's divisible by 3. Right, so those are things, numbers we want to get rid of. Now, how many of them are divisible by 2? Obviously, it's 100, because 200 divided by 2. How many of them divisible by 3? So we know 66 are divisible by 3, right? Okay, so it's 200 divided by 3. So that's 60, 18, 20, 60, 62. Okay, and there, of course, we know there's overlap. Right? Let's see here, there's overlap. What is overlap? The overlap is divisible by both 2 and 3. So that means divisible by 6. So both 2 and 3, right? Okay, how many of them? And we can calculate. We'll see this will be 33, because 200 divided by 6. Okay, so 33, right? Okay, and then from here we know, so from here what we get is what? The number of positive integers between 1 to 200 that are divisible by 2, 3, or 2, right? Divisible by 3 or 2. So those are not valid. How many of them? So we have equals 100 plus 66, but you have to minus the overlap, 33, right? So you get this 133. So those are not valid ones, right? But what you want is not divisible. So from here, we just get, should be total 200 minus 133, and we get is 67. So if you look at the part of integers between 1 and 200, there are 67 of them that are neither divisible by 2 nor 3. Okay, that's what we are looking for. Question number 6. Alice was computing the product of 2-digit numbers. She mistakenly loaded the number 5 by 7. Load the number 5. Okay. She mistakenly loaded the digit 5 in one of the numbers as 7 and got an answer to 3,268, right? What should be the correct answer? Now, let's see what the problem really means. Okay, well, you see, this basically tells us we want to write this number as the product of two-digit numbers, right? And one of them contains digit 7, because by mistake, you load the 5 in the original one by 7. One of them contains, let's say this one contains 7, right? Has a 7. Okay, has a 7, has digit 7. In other words, what we need to do is you see, this is just reduced to what? We want to factorize 3,268 as the product of two-digit numbers, right? And one of them has that digit 7, and one of them has digit 7, right? Okay, let's do the factorization. 3268. Let's use the division. Obviously, this is even number, right? This is even number. And if you look at the last 2 digits, you realize the last 2 digits, 68, is 7 times 4 times 17. So that means this guy is divisible by 4. Okay, so let's see. So if we divide by this guy 4, this will be 8, 117. So it's 4 times, so we get 3,268 equals 4 times 817. Now that the issue is we have to further factorize this, because we already know this guy can be written as the product of 2-digit numbers. So that means we have to further factorize 817. Well, the other problem is when you first look at this, okay, can we apply other divisibility tests? Unfortunately, no, at least for those simple ones, because if you add those together, it's not divisible by 3. This is not 0 and 5. Also, it's not divisible by 11. So we have to use some other methods to find the right decomposition. You see, the last digit is 7, right? And we ask ourselves, how can we come up with digit 7? Well, 7, if you want to come up, there's only 2 ways. There are only 2 ways. One is either you go with 2-digit is 1 or 7. Okay, so what we need to do is here, I want to write this guy as the product, right, of two-digit numbers. I try to do it. Well, then, in order to get a 7, either you can do 1 and 7. That's one way, or you can do 3 and 9, right? So that's another way, because 3 times 9 will give you 27. Okay, and then you just tune the numbers a little bit. You will get this. It will be 19 times 43. So that's work. This one works. Okay, so we get this one equals 43 times 19. Okay, and this gives us, let's go back to this original number. So this will give 4 times 43 times 19. But then you see, what we want is we want to write this as the product of two-digit numbers, and one of them has digit 7. How can we come up with 7? When we look at the 3 numbers a little bit, it's okay. So the way we can do is, if I multiply this together, I will get what? If you multiply this 2, 4 times 19 is what? Is 76, right? Okay, so then I just get this one is 76 times 43. I get my decomposition, right? Okay, now the original now one, what it should be the original one. Okay, now we look at the original one. Because the 7 is a mistake here, we have to replace the 7 by 5. So it's being 5, 6, 7 has to go to 5. So it should be 56 times 43, right? Times 43. And let's just calculate this one out, and you will find 46 times 3, and this equals to 2,408. Okay. Problem number 7. If the two 6-digit numbers 20AB20 and 12345B have the same remainder when divided by 9, find the sum of whole numbers C such that the 6-digit number AC is divisible by 9. Okay, so here we are dealing with numbers that are either divisible by 9 or they have the same remainder when divided by 9. So first of all, let's recall the divisibility test for 9. All right. Okay, so here we have the divisibility test for 9. All right, let's recall a number is divisible by 9 if and only if the sum of its digit is divisible by 9. Okay, so n is divisible by 9. Divisible by 9 if and only if a sum of its digits is divisible by 9. In fact, we can actually say more. All right, so here's something more. Okay, and when divided by 9, more. Okay, so this is more than the divisibility test for 9. All right, when divided by 9. When divided by 9, n has the same remainder as the sum of its digits, Okay, therefore, let's say we assume this is correct, right? So this is more general than the divisibility test, right? So let's remember this. When divided by given any integer number n, when divided by 9, the remainder of n is the same as the sum of the digit. Okay, so then we have so this one tells us 20 AB20 and 1, 2, 3, 4, 5 B. They have the same remainder, right? So have the same remainder. Okay, and then by this, okay, that just means if you add all the digits together, 2 plus 0 plus A plus B plus 2 and 1 plus 2 plus 3 plus 4 plus 5 plus B have the same remainder when divided by 9. When divided by 9. Okay, all right. We can write this. So this is just A plus B and plus 4, and this one is B plus. This is B plus 15, right? So this is B plus 15. Okay, all right. Well, now let's also recall a basic fact. Suppose I have two numbers, let's say m and n. So if n and n have the same remainder, when divided by 9, then from here we can get the remainder just means the leftover, right? If you divide n into piles of 9 items, then the remainder just are left over. Okay, now if they have the same remainder, then implies the difference is divisible by 9. This is understandable because when I take the difference, the same remainder or the same leftover is cancelled. Well, more precisely, you see if n, say n is 9 times something plus the remainder, right? And n is 9 times nothing plus the same remainder, right? Plus the same remainder. Now, if you take the difference, you see, if you take the difference, then the remainder, because they are same remainder, they cancel with each other. What left is a multiple of 9 minus another multiple of 9, and that, of course, is still a multiple of 9. In other words, n minus n is divisible by 9. All right. Okay, so then from here we'll get, because these two guys, they have the same remainder, we use this basic effect. If you take the difference, so that we had a plus b plus 4 minus b plus 15. This one is a minus 11. This one is divisible by 9, right? Okay, and then we should quickly get what shall be the remainder when a is divided by 9. We say, okay, so that means a has remainder 2 when divided by 9. Okay, so we get the first thing. We get a has the remainder 2 when divided by 9. Now, let's look at the second thing. So it says this one. So AC, this is divisible by 9, right? Okay, what does this mean? This one just tells us, again, we just look at the sum of digits, right? So this is straightforward application of divisivity test for 9. All right, just add it together. So it just means a plus c plus a plus c plus a plus c. So this is 3 copies a plus c is divisible by 9. And this just means, because we already have 3 here, 3 times a plus c divided by 9, this just means a plus c is divisible by 3, right? Divisible by 3. Now, what do we know? We know that a, when divided by 9, the remainder is 2. So this just means what? This means a, when divided by 3, the remainder is also 2. Okay, so we get a has remainder 2 when divided by 3. Okay, because you see, this one just tells us what? Tells us a equals 9 times the number plus the remainder 2. But this part, you see, this is just 3 times this, right? So divided by 3, the remainder is also 2. Okay, all right. So we get a has the remainder 2 when divided by 3, but it also require a plus c is divisible by 3. So this tells us c, when c divided by 3, right? Okay, so then we get c divided by, so we get, so a, the remainder is 2. So we get a c has remainder 1 when divided by 3, right? When divided by 3. Because a, when divided by 3, the remainder is 2, and a plus c is divisible by 3. Then the remainder, when c is divided by 3, the remainder has to be 1, right? Has to be 1. And then we say, okay, all the possible choice for c, we get c is 1 or 4 or 7. Now, if you add them together, so the sum equals 1 plus 4 plus 7, which is 12. All right. For this problem, let's quickly review this the solution of this problem. Here we use the main thing we use is the divisibility test for 9. It says a number is divisible by 9 if and only if the sum of digits is divisible by 9. But we also use, which is kind of a more general version. It says given number, if we want to find the remainder when this number is divided by 9, again, you can just look at the sum of its digits, and that you find what is the remainder of the sum when divided by 9. It is the same as the remainder of the original number when it's divided by 9. Okay, all right. So this is a more general version than the divisibility test. Problem number 8. How many different order pairs or partial integers m and n, satisfying that the GCD of n and n is 4, and the LCM of m and n, which is the least common multiple, is 1440. Okay, now let's look at this. Okay, so suppose this is the number n, right? And then here we have another number, which is n. They have a common, greatest common divisor, or we say GCD, GCF, greatest common factor is 4. And then the least common multiple is 1440. All right, so we have another number multiplied by 4, which is n. And then we have another number multiplied by 4. This one equals to n. Okay. Let me use another one to it. All right. Now we want this, the LCM. Okay, what is the LCM, right? So we have the LCM will just be this box times 4 and times this. Okay, so this is the common part, which is the GCD. So this is 144. So from here, we have this one multiply this, and this equals to, you divide by 4 is 360, right? 360. Now, another way to look at this, here I described this by the picture. Another way to see this is we can use algebra, right? So, okay, because the GCD of this, right? Another way to see this, you see from GCD is 4, we will get n has to be 4 times some number k, and n will be 4 times some number l, right? And the GCD of k and l, they has to be 1, because otherwise k and l, they'll contribute another factor. The GCD will be more than 4, right? Okay, and then we know the LCN, that the LCN of m and m will just be the LCN of 4k and 4l, and you can pull the 4 out. So this will be just the 4 times the LCN of k and l. Now, because the GCD of k and l equals 1, so this will just be 4k and times l, right? Basically, if we use this picture, so this is just the square here, and this is just the triangle here. Anyway, so from here, you get this one is 140, and you get a KL is 360. But this is just another way to describe what I put it here, right? Okay, now let's factorize this, right? Let's factorize this. So we factorize this. This one equals 8 times 3. Right. Okay. So let's see this. So this 100 and divide by 8. This is 4, 2, and this is 45. So 3 squared and times 5. All right. Now let's see. Here we have three parts. They correspond to different prime numbers. 5. The thing what we want is we want let's look at this, right? 3 to the 8. We can only either this whole thing goes to there, or either this or this. And we cannot split. We cannot do, oh, okay, so 2 squared goes to that and 2 goes to this. This is not possible because they are common. The greatest common divisor is 4, so we cannot split anything else. All right, so that's what we have. So that means, let me repeat. Okay, so that means either this one goes to this or this one goes that. And then we also have either this one goes to this or this one goes that, right? Or this one goes 5 go there or 5 go there. Okay. Now, the question is how many different ways, right? So we say, all right, so the question reduce how many different ways, how many ways can we distribute these 3 things, 8, 9, and 5, right? One way, so method 1, you can say, okay, let's just list out all possible situations, right? Just list everything out. So list everything out. Okay, so this is, you can do it, but just not efficient. Method 2, we can use the multiplication principle. Multiplication principle, right? Okay, now multiplication principle, we'll talk about this in details when we go to the practice about permutation and the combination, the counting problem. But for now, let's quickly review. What is the multiplication principle. See, we have 2 ways. So first of all, let's look at this, right? A multiplication principle just says, suppose I have a task to do, right? I have task to do. Let's recall the multiplication principle. Say I have a task to do. Task. We have 1 way. So let's step 1. Say we have 2 ways to do it, and step 2 we have 3 ways to do it, right? 2 ways and then 3 ways to do it. Then the total number of ways just equals 2 times 3, which equals 6, right? So this is called multiplication principle. So we look at the whole thing into several steps, and each different steps have a different number of ways to do it. Then the total number of ways to finish the whole thing is just multiplying together, right? So this is called multiplication principle. Now here says step one, we say, okay, let's arrange, see how many ways we can put 8. We have 2 ways, right? Either go there or go there. How many ways we can put 9? Again, 2 ways, either go there or go there, right? And how many ways we can put 5? Again, it's 2 ways, either go there or go there, right? Okay, so by multiplication principle, we know in total is just multiply together. In total, there are 8 different ways we can distribute these 3 things, right? For example, one way, right? For example, one way I can just, let's say we can say 2 goes to this, and this 2 goes to that, right? So this is one way. So that ends up with 8 times 4. This will be my n, and the other one will be 3 squared times 5 times 4. This will be my n, right? So this is one example, right? You can check the GCD is 4 and the LCM is 1,440. Question number 9. A certain positive integer has exactly m factors. 2 of these factors are 15 and 21. What is the sum of these 8 factors? Here, let's recall how we compute the number of factors. So let's recall. Let's recall this. So let's recall how we compute the number of factors. Let's use 100 as an example, right? Let's use 100 example. Step 1, we do factorization. So step 1, we do factorization. Okay, so we can factorize 200 as 2 squared and times 5 squared, right? Prime factorization. And then you see, if we are looking for its factors, let's say n is a factor of 100, then n has to be 2 to some power times 5 to some power, right? It cannot contain any other prime factors. Otherwise, it cannot be a factor of 200. And then we see, okay, what could be the power of 2? Because it's a factor of 100, and for 100 the power is 2. Therefore, this one cannot go beyond 2. So it is 0, 1, 2. And how about this? Similarly, this cannot go beyond 2. So it will be, again, 0, 1, 2. All right, that means here we have 3 choices. We have 1 plus 2 plus 1 choices. And here again, we have 2 plus 1 choices. Again, we use multiplication principle, get the number of factors of 100 equals 2 plus 1 times 2 plus 1, which equals 9, right? Which equals 9. And here, the reason I single out the 1 is because, don't forget, we can put 0 here, right? We can put 0 here. All right, so this is basically the formula, how you compute the number of factors. You just, the power of this plus 1, and the power of this plus 1, and then you multiply them together. Now let's look at our problem here. Here says this number n, right? It has 8 factors, and 2 of them are 15 and 21. So 15 what? This is 3 times 5, and this is 3 times 7, right? 3 times 7. Okay, let's see. If I write 3 times 5 times 7, how many factors do we have? Here the power is 1, here the power is 1, and here the power is 1. Then we get the number of factors is equals 1 plus 1 times 1 plus 1 times 1 plus 1. As I said, when we do the formula, you don't forget. So you have those powers here, right? Yeah, those exponents with the power here. But then don't forget, you also need to add 1 here. And okay, so then we get is exact 8. All right, so then the thing is, that's exactly, if we just use 3, 5, 7, and that's exactly the number we are looking for, is 8. You cannot multiply any other thing. You cannot have more powers of 3. You cannot have more power of 5. You cannot have any other prime numbers. Otherwise, you increase the number of factors. Okay, all right. So so we get the n. that's the end. Here is what we have, right? Okay, and then we can just find all those 8, let's say all those 8 factors, right? Okay, so we have 1, 3, 5, 7, 15, 21, and 35, right? And the last guy, it's just the itself, it's 105, right? Okay, so this guy is 105, right? It's 105. Now you just add them together. So this is what we're looking for, and it's 192. Problem number 10. N is the largest perfect square that is a factor of 9 factorial. And what is the 9 factorial divided by n? Here, what we need to recall is how we tell whether number is a perfect square. Okay, so let's recall the factor. Let's say suppose let's look at those prime perfect square. Let's say 100, right? We do prime factorization. So let's do the prime factorization, and this is 2 squared times 5 squared. And you see here the powers, they're all even numbers. And then you can also do, let's say 64, right? 64 is 8 to the square, which is 2 to the 6. And you see, okay, so this guy is an even number. All right, so what's the point? The point is a number is perfect square if and only if all the powers or all the exponents in its prime factorization are even number. Okay, let's say here, a number n is a perfect square. If and only if all exponents in its prime factorization are even. Okay, all right. Then let's do the prime factorization of 9 factorial. All right, so what's the 9 factorial? 9 factorial is 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9, right? Let's write out its prime factorization. Okay, it's obviously 2 is its prime factor. How many power do we have? So here we have contributed 1, here I contributed 2, here I contributed 1, and here I contributed 3. Okay, so it will be 1 plus 2 plus 1 plus 3, which is 7, right? Okay, so 2 to the power 7 and times 3. 3 will be contributed 1 here, contributed 1 here, and contributed 2 here. So 3 to the power 4. And then, of course, we multiply is 5. It's just 1 5 here and 1 7 here, right? Okay, so this is 9 factorial. And we are looking for n is a factor of 9 factorial. And then we're looking for the largest perfect square. But remember, for perfect square, all the exponents has to be even. And therefore, you see, so this is 2 to the 7, right? It has to be 2 to the something. So it's 2 to the even number. And I want it as large as possible. Okay, so it has to be to the 6. And then times 3, but 3, this is already even. Okay, so this is even, right? It's even. So point is, remember, this has even, and this has even. 5 and 7, this is 1 and this 1, they're odd, and you have to get rid of, because if you go down 1, just get 0. All right, so then the other just 1 times 1, right? Times 1, and there's not much you can do about it. So which is just 5 0 and this 7 to 0. Okay, so that's your n. And then you see 9 factorial divided by n. What you get? What you get is you just do the division, and you see what you have is that this just cancel with each other, right? Here I just cancel, get 1 2. So okay, so what you end up is 2 times 5 times 7, which is 70, right? 70. Okay, problem number 11. For how many positive integer n, the remainder is 8 when 128 is divided by n? Okay, 128 divided by n, so it's n times something, right? This is the quotient, right? And then plus the remainder, the plus remainder is 8. Right, so this is the algebraic expression that says that when 128 divided by n, the remainder is 8, right? Okay, and from here, we quickly get if you minus 8 on both sides, I get 120 is n times this. Okay, so this just tells us n is a factor, right? Or we say divisor of 120, right? 120. All right, now let's see what is the number of factors of 120. How we do it? Remember, we have two steps, right? Step one, we do prime factorization. So it's 120 is equals to 3 times 3 times 5. And then we get a number equals, then step two, right? By this, then we apply the multiplication principle. We say we have the formula, right? We have the formula. You see here hold on. Here's 3. Here the power is 3. Here the power is 1. Here the power is 1. Then the number of factors, the number equals the number of factors is 3 plus 1 times 1 plus 1 and times 1 plus 1, which is 16. However, all right, so here what we have is the number of factors is 16. However, we cannot use all those 16 factors because this one is the remainder. We must have the remainder has to be less than n, right? It has to be less than n. So what we are basically looking for is what? So we are looking for is the number of factors of 100 that are greater than 8. Okay, all right. Let's see. Those are no greater. Let's see what are the factors that are no greater than 8. Let's say, okay, we have it's 1, 2, 3, 4, 5, 6, and 8, right? So those are the factors of 120 which are no greater than 8, and they are not valid. So those we have to get rid of. In total, here we have 7, right? Have 7. And then we get the number 16 minus those invalid ones, minus 7, we get is 9, right? We get is 9. Problem number 12. How many numbers between 200 and 100, how many numbers between 100 and 200 can be the sum of four consecutive integers? Okay, so first let's see when a number can be written as 4 consecutive integers. Okay, so step one, well, just when an integer can be written as the sum of 4 consecutive integers, right? Okay, all right. Well, let's see if I have 4 consecutive integers. So this n and n minus 1 and n plus 1 and n plus 2, right? So this is the general way to express 4 consecutive integers, right? All right, if you add them together, you say, okay, if I add them together, what do you get? You get 4 copies of n and 4n plus 2. Okay, what does this tell us? Well, what does this tell us? It tells us a number can be written as a sum of 4 consecutive integers if and only if the remainder is 2 when it's divided by 4, right? So it's okay. And we here get this implies it has to be okay, here's the conclusion. Let's write down the conclusion. So what's the conclusion? The conclusion says n is the sum of 4 consecutive integers if and only if n has remainder 2 when divided by 4. Therefore, the problem is basically asking us how many numbers between 100 and 200 when divided by 4 has to remain 2, right? Okay, so now we just need to look at between 100 and 200. How many of them has remainder 2 when divided by 4? Okay, so the first one will be 102 and 106. And then you go to the last one is 196, right? 98. And how many of them do we have? Okay, so this is just 4 times 25 and plus 1. And this is 4 times 49, also plus 2, and plus 10. And we get, okay, we get the total equals 25 all the way to 49, right? So it's 49 minus 25 plus 1. So we get it's 25. So there are 25 numbers between 100 and 200 that can be written as the sum of all consecutive integers. Here the point is, the main thing is the first conclusion. An integer can be written as the sum of 4 consecutive integers if and only if it has a remainder 2 when divided by 4. Problem number 13. What is the remainder when this number n, all right, so n is right here, okay? When the number n is divided by 100. You see, when you're looking for the remainder divided by 100, this is just equivalent to asking the last 2 digits, right? Just last 2 digits of n, right? Now, how we find the last 2 digits of n? For this problem, the quickest way is to find a pattern. How we do it? Let's find pattern. For 5 to the 2.2, this one we know if you look at the powers of 5, it's very easy to see the last 2 digits has to be 25. Right? It's always, it remains like that. Okay, now let's look at the 7. Let's look at 7. 7, we know, let's try 7. So 7 and 7 squared, 7 to the 4 and 7 to the 5. Okay, we'll try to identify the pattern. So this is like 0, 7, right? So this is 49 and times another 7, 3, right? 40 times 7, 4, okay, right? Okay, so this will be 43, the last 2 digits. We're just looking for the last 2 digits. And then another 4 will be 0, 1, right? It will be 0, 1. Okay, 0, 7. So you see, what happens, it's a 4 cycle. It's a 4 cycle. Oh, hold on. What do we have? It's a 4 cycle. And then if we try to look at 7 to 22, 22, if you divide it by 4, right? 5, 20, and this is 2, 0, 20, and 5, 20. The remainder is 2, right? That get the remainder is 2. And therefore, it's because the remainder is 2, right? And this is 49. Okay, so the last 2 digits of this one is 49. The last 2 digits of this one is the last 2 digits of this one is 25. Okay, it's 25. And then if you combine together, this is the sum, right? So the sum, the last 2 digit will be 25 and plus 49. So we get is 74, right? Problem number 14. To encode a message, James first replaced each letter within the message with its corresponding numbers, where A is 1, B is 2, and all the way Z is 26. Next, which is we call one operation. James multiply each number by 3 and then subtract 5 and continue this process a total of m times. For example, when n is 2, the letter D is encoded to the number 16. If James encoded a 4-letter message, let's say 1, 2, 3, 4-letter message to the 4 numbers, 367, 205, 853, 1359. What is the value of n that he used, right? So each 1 time, and then he did twice, he did 3 times, blah, blah, blah. How many times that he used. Okay, here, let's first clarify what the problem says. Each operation, say you have a number, right? So you have a number n, and then after 1 operation, so if this n equals 1, just 1 operation, it goes to, we say this is called forward, right? For 1 operation, it will go to 3 times n and subtract 5, minus 5, right? For example, if you start from D, right? It's okay. If you start from D, D started from is 4, and then you go 1 operation, n equals 1, will be 3 times 4 and minus 5, that is 7. And then you do the second time, which is n2, right? You use you just do it again. Will be 3 times 7 minus 5, and then this gives you 16, and such and such. Okay, now what we know is we know eventually it end up with four numbers right here, right? So this is the four numbers, and we want to recover the original letters, and also we want to see how many times it has operated. Okay, so then of course what you go is you go backward. What we should do is we go backward, right? Backward, that means let's say I have number n and you go backward. If you go backward, that means you have to n plus 5 and you divide by 3. Okay, let's see. We first go backward one time, right? Go backward. Here, what we do is we go backward. Look at 367. Let's look at this. So 367 plus 5 and divide 3. What do we have? Is 372 and divide by 3, right? So we say get 124. So this is how we get 124 here. And similarly, you do go backward and those things, and then you go backward again, and then go third time, and then you go fourth time, right? You just write all the numbers out, and then you see that's what we have. Now already, if you see those numbers, they're already is between 1 and 26, and then we ask ourselves, are we able to do any further down? Can we go any further down here? The answer is no, because if you want to go further down, let's see, look at this. What will happen if you go further? Let's suppose we do n5 one more time, right? And then this will be 7 plus 5 divided by 3. This one is okay. This will be 4. This one will be 5 plus 5 divided by 3, which is 10 over 3, which is not, this is not integer. It's not integer. Okay, so that means we cannot go any further down. So can not go any further down, right? All right, that means we should just stop here. So this is, we should stop right here, right? Okay, and that's, so the value of n equals 4, and if these 4 letters will be, we say, okay, go back, so 7 will be A, B, C, D, right? So you say, okay, A, B, C, D, E, F, G, right? We can get this is 1, 2, 3, 4, 5, 6, 7. So this letter will be G, right? And this is 5. That means this letter will be E, right? And you can similarly, you can pick find 13 and 19, right? You can just we can let's say G, H, I, J, K, right? You can just find 13 and 19. Go to the list. Okay. All right. Problem number 15. What is the average of the all multiples of 16 between 1 and 1,000? Let's see. Let's look at all the multiples of 16 between 1 and 1,000. The first one, of course, is 16 itself. Next one will be 32. And then what is the last one? Let's see, when you do find the last one is we do the division, right? So we say, okay, 1,000 divided by 16. This should be 6, 9 is 6. 40, and this 2, and this is 2. Okay, so the last one will be 16 times 62. So that's the last one. The last one before 1,000 divided by 16. Okay, let's calculate out 16. So this should be 2, 7, and 62. Okay, so it's 992, right? Okay, so this is just 992. All right. Now, how we calculate the average? Right? Let's calculate the average. The average is the total sum, right? So this sum, which is 16 plus 32, and all the way to 16 times 62, and divided by how many do we have, right? So the number of the sum divided by number. Number is, you see, this is 16 times 1, all the way to 16 times 62. Okay, so we have 62 here. How we calculate the number of sum, right? Let's calculate the number of sum here. We use Gauss formula. We use Gauss formula, right? By Gauss formula is the first one. So the first one and the last one add together. So it's 16 plus 16 times 32, which is 992, right? Add together and multiply the total number of numbers here, we stick 3, and divide by 2. So this is Gauss formula, right? The first one plus last one. Multiply how many numbers do we have? Sorry, 62. How many numbers do we have here, and divide by 2, right? And then again, of course, you divide in order to get the average, you divide by the number again. And then here is cancel with each other, right? So what you get is, okay, just the half of the first one plus the last one, right? So this is 2, 1008 divided by, so it's 504, right? 504. From this computation, we basically get a rule, right? If we have arithmetic sequence. So here what we have, so this you see is arithmetic sequence. Because each time you go up by 16, right? Now for arithmetic sequence, so the average, so here says what do we conclusion? Or we say conclusion. For an arithmetic sequence, regardless what it is, the average, it just equals half of the first one plus last one, because it's just the first one plus the last one and divide by 2 right here, right? So this is the average. For this particular example, you see the average is just the first one plus the last one divided by 2. Okay. And this is the general rule. Question number 16. Here again, we are dealing with arithmetic sequence. Okay. Also, here we have an array of numbers. It says along each the numbers in each row must form arithmetic sequence, and the numbers in each column and also form an arithmetic sequence, right? Look at it here. So this arithmetic sequence, 1, 2, 3, 1 to 4, 4 to 7, and 7 to 10. Each time you just add 3 as arithmetic sequence. And this also has to be arithmetic sequence, right? Okay, now look at 10 to 36. So it's 10, this is 26, right? And you add twice, so divided by 2, which is 13. So each time you should add 13. Right? You should add 13. So this will be 23. And this you add 13. You add each time you add 13. Add 13. So this is 49. Now again, this one also is arithmetic sequence, right? So this is also arithmetic sequence. And let's see, each time you add this, and then add this. Now 49 minus 25 is 24, and 24 divided by 2, right? Divided by 2 is 12. So that means each time you add 12, you add 12 to it, right? Each time add 12. Okay, so then we get x minus. So you have the minus. Okay. Here is you minus 12, or the other way. You can do the other way. Hold on. So this is minus 12, or you say you do other way. Okay, so this is add 12 and this is add 12, right? Okay, and then you get x. The x will be 49 minus 12, so which is 37. Okay. Question number 17. Starting with the number 0 on my calculator, and I do calculation in 5 steps. Step 1, step 2, step 3, 4, and 5. Okay, so this is steps. Step 1, step 2, step 3, 4, and 5. At each step, I either add 1 or multiply by 2. What is the smallest number that cannot be the final result? Here you can look at those numbers and you find 11 is the smallest one that cannot be the final result. For example, you say, okay, let's say how can we get 10, right? All right, so how can we get 10? For 10, what I can do is, let's say the last one will be 10. And that means the one before it has to be 5 because you get it multiplied by 2. Okay, then how you get a 5? The only way you can get a 5 is you go 4, right? We just go backward. We get a 4. And a 4 plus 1 will be 5. Because each time what you do is either you add a 1 or you multiply by 2. And how you get 2? How you get 4? Well, what you can do is for this scenario we can use 2, right? It's okay if it's 2 here, right? If it's 2 here, and then you can just multiply by 2 to get a 4 here, and then the first one will be just 1, right? So first step, that means you just add 1, right? Add 1, and this is also add a 1. Add a 1. And 1. So this is example. How can you finally end up with 10? Similarly, you can also get the 9, 8, and 7. And you can see the only one you cannot get is 11. And actually all the others like 1, 2, 3, 4, 5, you can all get those numbers. And the first number you cannot get by this operation is 11. Number 18, what is the largest integer for which each pair of consecutive digits is a square? For example, right, 116 is such a number whose pair of, if you look at 116, right, you see this pair 16, this is perfect square. And then if you look at 81, this is also a perfect square, right? Of course, there are multiple such kind of numbers, and what we want to do is we want to find what is the largest one, right? We want to find what is the largest one. Okay, so first, let's list out those 2-digit perfect squares. Right, perfect squares. Okay, so what do we have is 16, 25, 36, 49, 64, and 81. And then we try to combine those numbers together to get the largest one to form, right? And yeah, you can check. What you can do is you just play around, and very quickly you will get is 81, 649. Because you see, okay, so you see this is a perfect square, 49. And then you have 64, this is also perfect square. And then you have 16, right? This perfect square. And the last one you have is 81, right? So this is also a perfect square. So that's the best we can do in order to get the largest such kind of number. Problem 19, if the page of a book contains 88, what is the least possible of pages of this book? Okay, well, we can first try to figure out how many 8 we have. Let's say from 100, from 0 to 99, right? So if we have from 0 to 99, we can get there are 28. And then from 100 to 199, again, another 28, right? At 20, at 20. And from 200 to 299, we get 20. And from 300 to 399, we get 20. Okay, now if you get all those 20 together, we have 80, right? And we need what? We need 8 more because this is 88. We need 8 more, right? We need 8 more. Okay, how you get 8 more? From 0 to 9, we have 1 8. From 10 to 11, to 19, we have another one, right? And then we say, okay, we want to from all the way to 70 to 79, we'll get a 1. That's exactly 8, right? We have 8 of them. We have 8 of them, and end up the last one appear is 78. Okay, so that means if we have the pages 400, so this is 400, right? 478. That's the best we can do, right? Which means the least number of pages of the book we need in order to get 88 8s, right? Okay. Problem number 20. Find the largest part of integer n such that this one is also an integer. So here we do is we do some algebraic operation. Let's see. So 2n plus 27 plus n minus 11. Okay. Let's observe this. So this is 2n and n, right? So what do we do is we say, okay, let's try to do a division that involves n minus 11. So how we do this? Well, I can just write this as 2 times n minus 11, right? And this is what? This is 2n minus 22, but I have 27 here. So that means I have to plus 49 here, right? I have to plus 49. So, okay, the point is this whole thing equals this one, right? Equal this one. And then you divide it by n minus 11. What's the advantage of doing this? The advantage is now we can actually cancel the term here, right? So we say, okay, I just get 2 plus 49 over n minus 11. What do we want? We want this guy to be integer. You see, this is already integer. That means we need this, right? We need this guy to be integer. Okay, all right. Therefore, what we want is 49 over n minus 1, this one to be integer. And the question is, we are looking for the largest one, right? What is the largest n? Clearly, the largest choice is n minus 11 equals to 49, right? So that's the largest we can do. And from here, you just quickly get n is 60. Right? Question number 21. How many n no greater than 1000 are there such that the following equations has integer solution x and y? Okay, so we want this one to be integer, to have integer solution. What we can do is, you see, so first of all, when you look at this, okay, we have two unknowns, x and y, but also we have a letter n. What we can do is let's pretend n is a number, right? We don't know what it is. We just try to figure out for what kind of number we can actually solve it, and we get, you see, we want to get its integer solution. Okay. Let's ask ourselves, how should we solve equation like this, right? So this is a linear system, right? 2x plus y equals n plus 10, and x plus 2y equals n minus 5. We have two unknowns. Obviously, what we should do, the general way to do is to eliminate one variable, right? We should eliminate one variable, right? X, so here x and y, two variables. Let's try to say, for example, let's eliminate y. So how should we eliminate y? Here, what we have is 2y, right? So, okay, so this is 2y. So what we do is we can multiply 2 on here, right? And this will give us is 4x, because 2 times this 4x plus 2 times y, so the 2y equals 2 times s 20. So this is 2n plus 20. Now let's look at this 2. Okay, well, so here we have both 2y. So what we can do is we take the difference, and this will get rid of one variable, right? By elimination, eliminate. Okay, so let's take the difference, minus, take the difference. So 2y cancel with each other. 4x minus x, so this is 3x, right? So this is just 4x minus x. And then this minus that, okay, so we have 2n plus 20 minus n minus 5, right? What do we get? We get n plus 25, right? So it's n plus 25. Okay, and then what's x? We get x equals n plus 25 divided by 3. And remember, what's the requirement? We want integer solution. So that means we want this guy to be an integer, right? We want this guy to be integer. Okay, so we need n plus 25 is divisible by 3. But what does that mean? That means just means n plus 1 plus 24 is divided by 3. But this is already divided by 3. So this just implies n has a remainder. So we need n plus 1 is divisible by 3. This just tells us we need the remainder to be 2 when n is divided by 3. So we need n. Okay, so here is eventually what we get. We need n has remainder 2 when divided by 3. So that's the requirement. All right, so now the question is just reduced to, okay, so this n has remained 2 when divided by 3. So the question is reduced to, okay, if you look at from 1 to 1000, look at all those integers, how many of them when divided by 3 has remained 2? And this is simple, right? You say, okay, it's a 2, and then you go all the way to, this will be 9, 9, and 8, right? So this is the last one. So this 3 times 0, this is 3 times 1, minus 1, right? And this will be 3 times 3, 3, 3, and then minus 1, right? Minus, always say plus 2. Let's say plus 0. So those are the collection. You can write this as 3 times 0 plus 2. You can write this as 3 times 3, 3, 2, and a plus 2, right? And then you quickly see how many do we have? We have 3, 3, 3, right? Because you go from, it's go from 0 all the way to 3, 3, 3, 2. So that's 3, 3, 3.